Great. Thank you so much for having me, and thank you for joining this talk. It's a real pleasure to be able to be here with you all today and learn so much about the large scale structure. And my goal today is to tell you about the cosmic microwave background as a large scale structure probe, and especially focusing on what the CMB can tell us about the baryons. And so I'll be talking about the baryons here, sometimes as a source of signal, but often as a source of bias and confusion when you're trying to learn about new physics from the large scale structure. And so I'm going to try to show you all the ways in which we can hopefully use the CMB to alleviate some of these baryonic uncertainties. So the short title for this talk could have been why, if you want to learn about your galaxies, you really should put them in the microwave. Um, so why should we care about baryons? This conference is about new physics. Shouldn't we think about new stuff, not the ordinary stuff that you and I are made of? And the reason to care about baryons is that you really need to understand them if you want to learn either new physics in cosmology or galaxy formation. And this is what this animation from the Illustrious simulation is trying to show you. So what you're looking at here in blue is the dark matter distribution. And so you see those dark matter halos and filaments. And soon in green and red, what you're about to see are the baryons. And so at first, it looks like the baryons are following the dark matter, but then when you look closely, you see all those explosions, these fireworks that are happening and are pushing the baryons outside of dark matter halos. And these fireworks that you're seeing have to do with supernova, so death of massive stars, and active galactic nuclei, so accretion onto black holes. And these are powerful effects that regulate galaxy formation. And so they're a source of negative feedback in star and galaxy formation. And the amplitude of those feedback effects is currently perhaps the largest theoretical uncertainty in our understanding of galaxy formation. And so, okay, this sounds like astrophysics, but I'll try to motivate why it's a problem for cosmology and new physics very soon. And this has to do with what has been called the missing baryon problems. And the baryons are not really missing, but the idea is that when you compare the distribution of dark matter and gas or baryons in the universe, what you find is that the baryons don't exactly trace the dark matter. They're typically more extended around dark matter halos. And in this talk, I'll use the words baryons and gas interchangeably. Usually what I'm talking about is the ionized plasma around those halos. And indeed, most of the baryons in the universe are in the form of gas, not stars. Um, and because of this feedback, which pushes the gas outside of dark matter halos, oftentimes you find that the gas is too diffuse and too cold to be seen directly in emission. And this is what has been called the missing baryon problem. Of course, the baryons are not missing, they're just a bit farther out. But if you could find exactly where they are and how they're distributed in space, this would be useful information for learning about the amplitude of these feedback effects. And you could learn a lot about galaxy formation. But if you don't care about galaxy formation, all you want to do is new physics with cosmology, I would argue you still have to understand what the baryons do. And what I'm showing here is a lensing cosmic shear power spectrum. So this is basically the matter power spectrum projected along a line of sight as a function of angular scales. And the different lines that you're seeing here are from different hydrodynamical simulations with different feedback amplitude in this galaxy formation. And naively, we know that baryons are 15% of the total matter in the universe. And so the power spectrum is the square of the matter density field. And so you might expect, if you know nothing at all about baryons, an uncertainty of about twice this, so 30% uncertainty on the matter power spectrum. And indeed, this is sort of what you see from all these different hydrosims. So they're all very sophisticated with complicated feedback prescriptions. But at the end of the day, the result is basically the same as if you said, I know nothing about what the baryons are doing on these scales. And that's a problem if you want to use those small scales, the scales of halos, in something like Euclid or Rubin Observatory to learn about new physics. And so to put it quickly, how are you going to analyze percent precision large scale structure data when 15% of the matter is missing or you don't know where it is? And indeed, because we have this theoretical uncertainty about what the baryons are doing on the scales of halos, the typical approach for the analysis of galaxy lensing data has been to basically just throw out all these small scales that we don't know how to model. So what you're looking at here is many, many curves. No need to look at each of them separately, but the impression I'm trying to give to you, this is from Cosmic Shear from DES year 3. Everything that's colored in blue or gray is data that is being thrown out because we don't know what the baryons are doing. And so the impression I'm trying to give to you here is like just what fraction of the data we're throwing out. Data points with very small error bars that contain a lot of information that we're just throwing away because we don't know how to analyze them. And so if instead we knew what the baryons are doing around the halos, perhaps we would be able to push those scale cuts to smaller scales and recover more information about cosmology and galaxy formation. Just to drive this point home very visually, this is again this illustrative simulation. And the little flecks of light you might be able to see here are the starlight from galaxies. But really, if you turn on other layers with baryons, so dark matter first and baryons, you see that there's a lot more to see around these halos than just the starlight. And a lot of these properties of the baryons, I'm going to argue we can actually measure using the CMB. And finally, just even more visually, if you look at night, you might be able to see the Milky Way and our nearest neighbor, or one of our nearest neighbors, the Andromeda Galaxy. And if your eyes could see all the diffuse baryons around the Andromeda Galaxy, it wouldn't look like a few degrees on the sky, it would look actually more like 60 degrees on the sky. And so this gives you a sense of just how much stuff there is to see that you don't typically see just in a galaxy survey when you're looking at only the starlight. And so how do we see these baryons? How do we alleviate this baryonic uncertainty in our modeling of lensing and large-scale structure? My goal with this talk is to show you how to do this using the cosmic microwave background. And so we often think of the CMB, this first light from the Big Bang, as telling us about the initial conditions of the universe, so that baby picture of the universe. But really, for us to see the CMB, those photons have had to travel all the way between the last scattering surface and us. And on their way, on this trip of 14 billion years, a number of things can happen to these photons. So the photons can bounce off. They can be Thomson scattering by the free electrons in the plasma, in those baryons around galaxies. The photons can be deflected by the gravitational pull of the large-scale structure through gravitational lensing. So very loosely speaking, you might think of those as shadows on the CMB. You have the CMB as the backlight, and you're seeing those shadows imprinted by the large-scale structure due to properties of the baryons through Thomson scattering and property of the total mass through gravitational lensing. And so there's a lot to learn about the baryons and the large-scale structure by looking through the CMB. And for the rest of this talk, I'll be focusing on these gas shadows, these scattering effects that imprint the gas density, temperature, and motion onto the CMB. So I have a bit of a crowded slide here that people who know me know that I sort of show it in every single talk. But this is kind of my one slide summary of all CMB secondary anisotropies. And so it may look intimidating, but if you know this one or if you take a photo of it, it has pretty much all you need to know about all the different CMB secondary anisotropies. And so in particular, there's a number of properties of the large-scale structures that are imprinted on the CMB. And those are summarized by all of these dimensionless parameters. So the size of the lensing deflection, about an arc minute, tells you about your gravitational potential and the total mass. How fast that potential changes with time, whether it's due to dark energy or due to the accretion of your halo. The optical depth to Thomson scattering, just how many free electrons there are. This is going to be the main probe of where the baryons are, how much baryons there are. What's the temperature of the electrons and the temperature of that gas? And then what are the macroscopic motions of that gas? So bulk motion, rotational motion, turbulence. And finally, some parameters that have nothing to do with the large-scale structure, but about the primary CMB that enters some of these effects. And so you can pretty much generate all of the different CMB secondary anisotropies by taking different products of all these terms. And so you can go on forever, but basically there's sort of two classes of anisotropies. The first ones have to do with gravitational potential. And so you probably have heard of gravitational lensing, integrated Sachs-Wolf, and its nonlinear counterpart, the Riesz-Schama effect, or the moving lengths. And so these are all have to do with the gravitational potential, so how much mass there is, or how that potential changes over time. And then the other big class of CMB secondary anisotropies has to do with Thomson scattering. And so you probably have heard about this thermal Sunyaev-Zeldovich effect and its relativistic correction, which tells you about how much gas there is and what the temperature is. And I'll be telling you as well a lot more about this kinematic SZ, which again is how much gas times how fast it is moving. And I'll probably just say a word or two at the end about the screening effect, how much gas there is. So this was my summary of CMB secondaries. And here's a completely unnecessary slide about how the CMB is not just primary anisotropies, not just those degree blobs about the early universe, but really when you look at the CMB, you get to see all these shadows that tell you about the silly person that's casting them. So more about those gas shadows and those scattering effects. For the rest of the talk, I would like to tell you how you measure these effects, what are some of the challenges with measuring them, all the things that we have tried to learn already from them, and what we need to do better to really put this on a firm footing. And just to reiterate, this image is actually to scale. This is a Hubble image of a typical galaxy of which we have measured the TSZ effect. And you can see again just how extended the gas is around galaxies. So I've told you about, oh yes. Oh yes, I'll show this to you in a few slides. But the scale of the dark matter viral radius would be somewhere around here for those halos, so several viral radii. So again, those thermal and kinematic SZ, these are what happens to CMB photons as they bounce off moving electrons in the plasma and bounce off to you. And I really think of those as kind of just Doppler effects. So you have a CMB photon, you have a photon bouncing off a moving mirror with that free electron. And so what you get is a Doppler term. And so when the whole plasma has a bulk velocity, you get this kinematic SZ. And it's a Doppler effect, so it depends on the velocity of the gas along the line of sight. And it depends on how good of a mirror your gas is, so just how much gas there is. But your gas also typically is hot and so has a lot of random thermal motions. And so you get to add these effects for all of the different electrons in your gas. And so because the motions are random, the first order term in velocity cancels, and to lowest order, you get a velocity squared term, which is a temperature. And so this thermal Sunyaev-Zeldovich effect tells you about how much gas there is again and how hot it is. And finally, I hope to tell you just a bit more about patchy screening. So how do we measure these effects? In the case of the thermal SZ, we're helped by the fact that it has a very specific frequency dependence that you can predict from first principles. And so what you can do is you can just build a map of that effect. And Will Colton in the room and many others are experts on how to do this. And then you can point your CMB telescope around the location of a galaxy that you know, and you can try to look for these shadows. And so for this kind of luminous red galaxy, you get a sense of what the resolution of our CMB experiment is. It's about this circle, and this is the typical viral radius, so where the dark matter is for those halos. But for individual galaxies or for galaxy groups, when you look at the CMB around your galaxy, what you see is basically nothing, just noise. And that's just because the signal is too faint for you to detect on individual objects for those low mass halos. And so one way to solve this is to just look at many, many, many more galaxies, a lot of galaxies. And when you add all these galaxies together, you stack them, you get to average out your noise. And you get to see those dark shadows around the galaxies. And so several points I would like to make with just this illustration is, again, this squared image here fits in the central pixel of our CMB map. And the resolution is nowhere near enough to resolve the galaxy, but it's good enough to resolve the gas. And the gas itself is more extended than the dark matter, which you see in this white line. And so I wanted to highlight the work of Henry Liu, who's a grad student at Berkeley, working with Simone Ferraro and me on this project, and who's working on a lot more SD measurements soon, I think with Urosh. That should be really exciting. And so what Henry did is he used CMB maps from ACT, which we heard about yesterday from Armenia, and a large galaxy sample from DAISY, and performed this stack. And to give you an idea, these are the measurements that I led 5 years ago, where you could start to see those shadows of the gas. And now with Henry's measurements, the precision is just a lot better, and you can clearly see this shadow. Something that probably catches your eye already and should worry you is why is the shadow not deeper at the center? Why does it look like a donut rather than a blob? And this has to do with contamination to our TSZ map, contamination from dust emission from the galaxy itself. And so that's actually a really important challenge to measurements about the thermal SZ from low mass objects, is that this thermal dust contamination needs to be controlled. And there are ways to do this, but it's really challenging. And so one way is to use the different frequency dependencies of thermal SZ and dust to try to remove the dust contamination. But this is subject to uncertainties. Yes. Yeah, I think this would be actually a really interesting thing to quantify. These are luminous red galaxies, and the sort of common wisdom was that these are not very dusty objects, and this was important for things like selection effects in redshift space distortions, because there's an effect where if they're very dusty, depending on their orientation, you might be less likely to detect them if their lights go through more dust, and this couples with some of the quadruple in RSD. And so a lot of the time, the common wisdom was like, oh, these are not dusty galaxies. It shouldn't be a problem. But here we can actually clearly see the amount of dust in there. And so I think there's something we should be able to say about the dust. We haven't really pursued this. One challenge is that here we're seeing the dust in emission in the microwave. For optical surveys, what's relevant is the dust extinction in optical. So there might be some modeling here to connect the two. But I think there is some handle here on the dust that could be useful to explore. Yeah. Thanks for the question. And so this is something to keep in mind if you're going to use the thermal SZ to learn about the baryons. If you're looking at very massive objects, you don't have to worry as much about the dust, so very massive clusters. But for the low mass halos that make most of the matter power spectrum, this is going to be a huge issue going forward. And so I'm now going to switch gears and tell you about the kinematic SZ effect. And perhaps I should have already told you why it's useful to have all these different effects. So they all depend on how much gas you have. But if you think you know what the bulk velocities are, then measuring KSZ and TSZ lets you separate how much gas there is and how hot it is. And so those are useful inputs for galaxy formation. But also, if all you care about is removing the baryonic uncertainty to lensing, then what you really want to know is where the baryons are, so the density. You don't really want to know density times temperature. You really want to know density, and this is one thing that KSZ helps you do. So how do we measure KSZ? One challenge is that you cannot simply do the same kind of stack as for thermal SZ. Two reasons for this. One, because it's an overall Doppler effect. It preserves the black body spectrum of the CMB, and so you can't use multi-frequency data to isolate the KSZ. And the other issue is that the KSZ changes sign depending on the bulk velocity of your halos. And so if you simply average the KSZ over many, many objects, your signal will cancel out and you'll get 0. And so to avoid that cancellation, you have several options. And the one that I'm going to present to you is using an external handle on what the velocities are. So if you know a priori what the velocities are, then in your stack, you can weight by those velocities and avoid the cancellation. And the technique we've used to know the velocities a priori is this velocity reconstruction from the matter density field. It's very much the same approach that's used in BAO reconstruction. And the way it works is simply through mass conservation. So in linear theory, velocity and the time derivative of density are related. And intuitively, what this means is just that if I have more stuff here, it's because stuff has been moving towards it. And so this may look like a very simplistic thing, but when you use this in linear theory, you basically get the Zeldovich approximation, which works extremely well on large scales to predict those motions. And for the purpose of our KSZ measurements, we need to know the performance of this velocity reconstruction. And so how well does the reconstructed velocity compare with the true velocity? And so this is something that we quantified in simulation. This is work led by grad student Bernardita Reed-Guachaya, working with me at Stanford, and Boriana Hajiska, working at Berkeley, and now just started at Cambridge as a professor. And in these two papers, Bernardita and Boriana used simulations where you know the true velocities of the galaxies and their host halos, and you can perform our velocity reconstruction and quantify how well it works. And so these plots are scatter plots between the reconstructed velocity and the true velocity per object. And crucial to understanding the amplitude of our KSZ measurement is this correlation coefficient between true and reconstructed velocities. And what these papers showed that was very interesting is that something that in hindsight should have been obvious, but we had missed, is that this velocity reconstruction, we should not think of it as reconstructing the velocities of the individual galaxies. They're actually much better at reconstructing the velocities of the host halos. And that should be obvious because this is a large-scale reconstruction. It does not capture the viral motions of galaxies inside halos. But for our purposes, it's actually exactly what we want because the KSZ cares about the bulk motion of the gas, not the random motion of that galaxy within the halo. And so when you actually compare the reconstructed velocities with the true one for halos instead of individual galaxies, what you find is this correlation coefficient is actually quite a bit higher, something like more than 70%. And this is the quantity we care about for our KSZ measurement. The other important result that came out from these studies is that if we used to think that if you want to reconstruct the velocities along the line of sight of your galaxies, you really need good redshifts. And intuitively, the idea is, if my galaxies are this way, they're going to move towards each other. If I got their positions wrong, I'm getting their velocities wrong. But in fact, the velocity fields are coherent on very large scales, something like 50 to 100 megaparsec. And that's a scale very comparable to the typical photo-Z error in a lot of these surveys. And so it turns out if you have photometric redshift errors, you only lose a factor of about 2 in signal to noise, which means you can get it back if you have more than 4 times more galaxies. So for KSZ, one spectroscopic galaxy is worth 4 photometric galaxies. And typically you have more than 4 times more photometric galaxies. Moving on, this is just a visualization of what these reconstructed velocities look like. And this is what they look like for bus, a measurement that I did many years ago. Color-coded in blue and red are patches of positive and negative velocities along the line of sight. And the largest sample you see here is what happens when you switch from bus to DAISY. And so now for each object, you have an estimate of the velocity, you know the position, and so you can stack with that kind of weighting. And so Bernardita and Boriana pursued those stacks, and switching from bus to DAISY, a much larger sample, increased a lot the precision of our measurements. So this is what I did many years ago with bus and ACT, and this is what you get now with DAISY and ACT. And so these are some of the highest precision stack KSZ measurements to date. We did a comparison between photometric and spectroscopic sample, and we were able to verify that rule of thumb that I told you about, how the signal to noise scales with number of objects. And a number of interesting things can be learned from just looking at these profiles, and I'll tell you more about this. I also wanted to address some questions that I often get about how can CMB possibly be useful to learn about stuff that's on such small scales. And so one question I often get is, isn't the CMB experiments resolutions typically way too low to be useful? And so typically what you find for these halos that are like large galaxies or small galaxy groups is that the virial radius is of order 1 arc minute, which is typically the size of our angular resolution. And the gas tends to extend several arc minutes. And so actually the resolution of our CMB experiments is pretty well matched to this problem. And in particular, the CMB experiments are good enough for probing the gas, the diffuse gas outside the virial radius, which is really hard to observe in any other way. And so here are some of the latest KSE measurements that are available if you're interested in analyzing them yourself. All of these are publicly available, and there's reference to where to find them in these papers. So feel free to use them in any way you like, and feel free to reach out if you have any questions about them. And so we have measurements for a number of galaxy samples in DESI currently, luminous red galaxies, this bright galaxy sample, emission line galaxies. We have them split by redshift, by stellar mass estimates, and other quantities. So you can start to ask questions about how feedback works. Maybe I'll skip this. Another question that I often get is, is your signal to noise in KSZ good enough for these kinds of studies? I told you my goal was to help analyze percent precision lensing data, and what I've shown you so far are sort of blobs in images about the gas. So is the precision sufficient? And part of the answer here is that since baryons are 15% of the matter, if you want 1% precision on the total matter, the precision you need on the baryons is not that large, only something like 7%. And this is basically the signal to noise we have right now in KSZ measurement. And that's only gonna grow. And so in a sense, we're almost already not statistics limited in those KSZ measurements. And so the whole challenge is now is how do we use these measurements to actually learn about galaxy lensing? And so in fact, to give you an example from our 2020 measurement, we were already able to answer a question, which was this small scale galaxy lensing being low. So the fact that on the typical scales of halos, if you predict what the lensing should be, this red curve, assuming that baryons follow the dark matter, you get quite a bit larger of a signal than you actually measure in those green data points. And with the signal to noise we had back then, which was around 10, we were already able to say that the theory curve for lensing should be corrected to this blue line, which accounts for part of the difference in this tension. And since then, the modeling has improved, where people are able to put those constraints on the correction to galaxy lensing and other things. So just to give you an example of the kind of things that we have been able to learn already from these measurements. Too many plots for me to explain in detail, but the fact that the gas is more extended than the dark matter, which is not a surprise, but nice to be able to confirm. The fact that the gas profiles we're seeing are already enough to explain half of the tensions that were seen on small scale in lensing. Combining KSZ and TSZ tells us about the temperature of that gas and how the temperature profile evolves as a function of distance from the center. And some very preliminary work about comparing the measurements we get to hydrodynamical simulations and finding mostly disagreement with most of the simulation, hinting at wanting more feedback or the gas being pushed out farther out. And so this is the latest version of this measurement. And I'm sorry, this is a paper from Bernardita Ridguachaya. I meant to write this here. And the way you should understand this plot is it's something like a cumulative profile as a function of radius, or close to that. And so the red data points are what we measure, and different lines are different simulations. So gray here is dark matter, and so indeed you find more gas on the outskirts than you would expect from the dark matter profile. And then if you look at these different colorful curves, what you see is different hydrosims. And you see that the ones that naively seem to match better our measurements from Illustris rather than TNG are ones that are normally thought of as having way too much feedback, the kind of feedback that would just destroy the galaxies themselves. And so those comparisons are a bit simplistic and preliminary, but they do suggest that perhaps we're about to learn something interesting about the gas, the feedback, and therefore the effects on the matter power spectrum on small scales. But I'll say more about some of the challenges in drawing those conclusions. So again, probably too many plots, but I just wanted to highlight the fact that many studies have started in the direction of joint analyses between lensing and those baryonic information from KSZ and other, in order to just tackle this issue of what happens to the matter power spectrum as a function of scale. And so in all of these plots, what you can see is a colorful band that represents the suppression of the matter power spectrum that you seem to infer if you include the corresponding baryonic information. So this is weak lensing alone, trying to add some X-ray information, some stacked KSZ profiles, both, and various combinations of them, as well as CMB lensing. So I think there's a lot of interest in trying to do this, and we're all sort of doing baby steps in this direction. And so in the rest of the time I have, I would like to tell you about what the challenges are in modeling this KSZ to learn about the small scale matter power spectrum and the things you should be looking out for from all these studies. And so the first point I want to make is if you try to use something like KSZ to solve the baryonic uncertainty for something like galaxy-galaxy lensing, so where you cross-correlate galaxy positions with shear, that one is a very well-posed problem and one where the modeling is not challenging, I would argue. So when you do galaxy-galaxy lensing, you stack the shear around galaxies, and you're getting the total mass profile of these objects, so dark matter plus gas. Now, we can stack the CMB maps around the same exact galaxies, and through KSZ, get the gas profile of the same exact galaxies. And because these are the same exact galaxies, what you can do is you can basically just subtract the two signals, and you'll have exactly removed the gas contribution to galaxy-galaxy lensing. And so in a sense, this is something you can do from the data itself with almost no modeling. And that's because you know you're looking at exactly the same halos. The galaxies have the same halo occupation distribution since they're the same. And the weighting with mass, if your sample has a spread of mass, is the same because it's roughly linear in mass. And so whenever you see studies that use KSZ to help the modeling of galaxy-galaxy lensing, this is usually pretty reliable and fairly model independent. You just have measured the gas and basically subtracted it. Where things get more tricky is when you either want to learn about galaxy formation or the baryonic effects on cosmic shear, which is the auto spectrum of the ellipticity of those galaxies, the auto spectrum of lensing. And the challenge with all our attempts to do this is that our KSZ measurements are typically only measured in stacking around some galaxies. And so you've measured the gas profiles of these galaxies, which live in some sort of halo masses at some redshift. But cosmic shear, the matter power spectrum or lensing power spectrum is an integral over all masses and all redshifts. And so in principle, if you want to solve the baryonic uncertainty for cosmic shear, you need to know the gas profiles around all halo masses and all redshifts. And currently, all of the studies you've seen have just stacks around one halo mass at one redshift. And so implicit in there is often a large extrapolation across mass and redshift, something that this nice paper made very clear. And so that's a challenge. And so moving forward, the signal to noise is getting sufficient that we can start exploring different masses and different redshifts. But this will be a challenge in our modeling. Something that may help, and I won't say too much about, is there have been claims of universality in the effects of baryons on the matter power spectrum, meaning that in a lot of those hydrosims that seem completely different in how they implement feedback, people seem to find that this is roughly still a 1 or 2-dimensional problem. Meaning if you tell me one or two things about, say, how much gas there is in halos of some mass and some redshift, those hydrosims all lie on a line about the effect on the matter power spectrum. And if this relationship is true, then this extrapolation may not be such a large problem. But I think at the moment, it's sort of an open question of whether this universal relation that seems to appear is really a physical fact or just the fact that all the different hydrosims, although different, are not different enough. And then another thing for if your approach is to use those KSZ measurements in combination with hydrosims to constrain feedback, and then use those hydrosims to tell you what the small scale matter power spectrum does. The challenge is that our KSZ measurements are again stacked around some types of galaxies. And are you able in the simulations to select a really matching sample of galaxies? So I'm comparing my measurements to simulations, but if these are not the same halos, not the same galaxies, they may not match, and that may not be telling me anything physical, just that I haven't matched the galaxies. And so currently, all the hints of large feedback that we seem to see in all our measurements when comparing to a hydrosim do rely on us having properly matched the galaxies in the sim and in the real data, which is extremely hard. And so I think a lot of progress is being made in improving this modeling, but I think a lot of work still remains to be done, and we're working on this. Right. So Mhm. Right. Oh, I see. So typically you have the overall e to the minus tau, and then you have the tau of those objects. And for us, for KSE, we really care about the tau of these objects. And so those hydrostims tell you where the gas density is. Most of that gas is ionized, but they usually also tell you an ionizing fraction. Um, oh, sorry. Yeah, in that case, oh, I see, I see, I see. So yeah, so in that case, for that tau for Thomson scattering, it's really not that model independent. It's really just the integral of the electron number density along line of sight. And I guess I should have written this. But yeah, those simulations tell you just how many electrons you have, and you can just integrate that along the line of sight. Um, it's not as complicated as, say, for the Lyman alpha forest. How do you get tau from the simulation, which I guess you've heard a lot about from Matteo. So yeah, those simulations kind of just tell you what the tau of these objects is directly. The question is, are you looking around the right galaxies in those sims? Okay. If I have just an extra couple minutes, maybe, yeah. I just wanted to tell you a bit more about this other effect, the anisotropic screening of the CMB. And this was work led by Theo Schatt, who's a grad student at Stanford, Abhishek Maniyar, a postdoc at Stanford, and starting soon as a CNRS faculty in ANSI, Will Colton, who's in the room, Nishant Mishra, who's now at Michigan. And this effect, the screening effect, is again Thomson scattering of the CMB by these electrons around galaxies. And I would call it this anisotropic screening in the sense that it's not just the mean tau that you normally see in the CMB power spectrum. Now it's an anisotropic screening because some line of sights have massive halos that just have more optical depth. And what this schematic is trying to show you is that this is how the effect works. So say you're looking at a hot spot in the CMB, you would naively expect to see those hot photons traveling all the way towards you. But what Thomson scattering does is that some fraction of these photons, maybe one out of these three, is going to be scattered outside of your line of sight. And at the same time, other photons that should not have reached you, some fraction of them are going to end up in your line of sight. And so overall, what happens is that some fraction of the hot photons you should have seen are being replaced by average CMB photons. And so what this screening does is it basically reduces the contrasts of your CMB images. So where you should have seen a very hot or very cold spot, you now see a slightly less hot or less cold spot. And this is summarized this way. And so this effect would be nice to measure because it probes the optical depth directly with no dependence on velocity. And so if you have this and you have KSZ, now you have a probe for the line of sight velocity field, which is really useful for sort of new physics on large scales, things like primordial non-Gaussianity. And so I just wanted to advertise this sort of cute estimator that we tried to come up with to measure this effect. And so again, here's a simulated CMB map where you see those degree scale hot and cold spots. And the little white patches you see here are exaggerated screening signal from galaxies, which bring the temperature closer to the mean, closer to 0 or white. And if I take a slice through this image, it might look something like this, temperature as a function of position. And so again, the black line here is what the primary CMB might look like, so degree scale fluctuations. And the little blips you see here are the screening, which brings the temperature closer to the average. And one interesting thing to notice about this effect, which is different from pretty much everything else, is that the temperature, the sign of this effect changes. It can be an enhancement effectively or a decrease in the temperature. And it changes in a way that's correlated with the large scale temperature. And so we use this effect to develop a new estimator for this screening effect, which basically just measures the small scale temperature fluctuations and the large scales and compares them to get at the optical depth. And so this was an interesting thing to forecast and implement on the data. One challenge, though, is that this turns out to be biased by CMB lensing in a way that can be modeled and subtracted. And so this was pointed out in a number of papers from Noah Saylor, who's in the room, I believe, and Boriana Hadjiska. And so once this lensing bias is subtracted, currently this effect is not detected, but really close, like 2 to 3 sigma. So I think we're probably very close to measuring this effect, which would be really neat. So to wrap up, the uncertain astrophysics of galaxy formation and feedback, which may not be something you want to learn about, is something you may have to learn about because it currently limits our small scale reach in large scale structure probes and especially in galaxy lensing. And the CMB does offer a fairly clean way to measure what the baryons are doing on these scales and therefore allow us to unleash our ability to learn new physics from the small scale large scale structure. So thanks for your attention, and I'll be happy to take questions. Right. Are you thinking about the large scale vorticity or on scale? Mm-hmm. Yeah, and so on the scale of the right, right. So yeah, so I think an interesting question, especially for astrophysics applications, is learning about everything about the gas in that halo. And so you have the density, you have the temperature from TSZ, you have the bulk velocity from KSZ. You can hope to measure the rotational, so the rotation of that gas through something that's called the rotational KSZ, which is really just saying that the KSZ on the right and left side of your halo might have a different sign. Blake and others in the room have made forecasts and tried to detect this effect. The turbulence, I think, is a bit harder to detect, but would be really cool, especially if you care about things like non-thermal pressure support in those halos. So that's a challenge. But for this, for example, something that does help is that if you measure the integrated thermal SZ in your halo, so you have density times temperature, that's kind of the thermal energy of your gas. So if you integrate this, you have the total thermal energy of your gas. If you know the gas density profile from, say, KSZ, and you know the gravitational potential profile from lensing, so you know the total gravitational energy of the gas. So if I know where the gas is and what potential it sits in, I can compute the gravitational energy. And then you can write some sort of viral theorem that's kind of just an integrated version of equilibrium. And this one normally connects the thermal energy of your gas to the potential gravitational energy of the gas and other forms of support. So in principle, in this way, you can infer whatever support there is that's not thermal. Um, so I don't think we can measure the turbulence directly, but you can get some insights on how much it contributes to the dynamics. Yeah. Mhm. Yes. Mhm. Mm. Mm. Yeah. Mhm. 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 Yeah. So yes, and so I was a bit loose about this missing baryon term, and of course, it's not that they're gone or missing. I think the main theory, as you say, is that they're currently in that WIM, this warm-hot intergalactic medium. And kind of one selling point of these approaches is that they're very well tuned to measuring this WIM. And part of it is that gas is fully ionized, and so it does Thomson scatter, and so it contributes to our KSZ and TSZ. Another selling point is, like you said, because it's diffuse, it can be hard to detect in emission, like through X-rays, for example, because that can scale as like density squared, whereas KSZ scales as just density. And because of that, it's well suited for those sort of low mass, low density, and low temperature environments, because KSZ is just density. So if you integrate the KSZ, you just count your baryons. So yeah, that was kind of our motivations when we started this a few years ago, was to just find this WIM. And as you say, I would probably not call it a missing baryon problem anymore today, because we sort of know where it is. But the real baryon problem is exactly how far is it distributed. Yeah, thanks. Mhm. So yeah, so in this case, um, when you do galaxy cross galaxy lensing, you really are measuring the projected mass profile of these objects. And so in principle, that mass profile is dark matter plus baryons. KSE will tell you exactly where the baryons are, so you can subtract that out. The effect that could be left out potentially is the sort of feedback of the baryons on the dark matter. So say I have AGN, push my baryons out, those baryons gravitationally pull on the dark matter and affect the dark matter profile. So that's something I cannot subtract this way because KSE is only measuring the gas. I believe this is sort of like a higher order kind of subdominant effect. So I think if that's the only thing I'm left with, I'll already be pretty happy with this. But I agree, I think it would be really interesting. I would really like to know how large that effect of the feedback of baryons on dark matter is. I know there's been quite a bit of work on this from Orel Schneider's group and others, but I'd like to have a clear number on that. Thanks. Mhm. Yeah, thanks. That's a really, really good question and something I should probably have addressed as well. Like, indeed, so a lot of these hydrosims are calibrated with galaxy luminosity functions and X-ray gas fractions from the pre-Erosita era. And modeling these X-ray gas fractions is actually not that trivial. And one shift we've seen in the X-ray measurements between the pre and post-Erosita is that um, those measurements have shifted towards what we see. And so we've seen those extended gas profiles since sort of like 2015. The measurements haven't really changed. But back then, the idea was that we were a bit outliers and this was a strange thing to see. And now this is actually quite concordant with what post-Erosita X-ray measurements seem to give. So that's interesting, yeah. Yeah. I agree. I think we don't exactly know that number, and that's sort of that's one thing we're working on with Bernardita is incorporating all these uncertainties in the modeling. So typically, currently, all the measurements that you have seen and that I have shown are things like this, where you have measurements and then you have a simulation curve, perhaps with an error band that tries to where people have tried to change a little bit the selection function of the galaxies in the hydrosim, but I don't think a lot of these are super fully quantitative. I think the group of Alex Amen and others have tried to improve this using galaxy lensing measurements that tell you about the mean mass of the halos, but I think it'd be interested to go beyond that as well. And so what we're working on at the moment is generating a bunch of possible samples of galaxies in hydrosims that match very different samples of the HOD of those galaxies. So in the case of DAISY galaxies, we have handles on the HOD, so which halos they live in, based on their clustering and based on galaxy lensing. And so what we're doing at the moment is sampling this HOD posteriors, and for each of them, producing a prediction from the hydrosim and comparing that to the data. Mm-hmm. 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 Um, yeah, so those measurements are those compensated aperture photometry filters. And at each of these points, yeah, intuitively, it's a bit confusing, but it's somewhere between a slope and a cumulative profile. Um, we don't necessarily have to do these, but yeah, sort of the halo, most of our signal to noise is around there. So it's not the very center of the galaxy group or the galaxy, but yeah, it's a few Virol radii. Hmm. Hmm. Right. So I think that's a really good point. So the case of galaxy lensing, so galaxy cross shear, is the one that's easiest for us to solve with KSZ. But you may argue that for cosmology, it would be easier to be able to it would be more convenient to solve the cosmic shear case, and that one is a bit harder. So yeah, in galaxy lensing, you can solve the baryonic uncertainty on small scales. There, you might argue that you also have uncertainty on the galaxy halo connection, so your bias expansion, for example, in EFT or your HOD. That's completely true. And one of the selling points of cosmic shear in lensing is that you don't have to worry about where the galaxies live and the HOD. And so that's a really nice thing. The flip side to this is that you have this integral over halo mass that's harder to constrain. And I don't know if maybe Blake has a. Mm-hmm. 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 Mm. Yeah, that's a good question. So I don't think I know enough about kits, but I think we have experts in the room, so I don't know if they want to chime in. Yeah, so mhm. Thanks. Cool. Thank you.